Today we're going to talk a little bit about Lewis dot structure stability and how it relates to resonance structures specifically. But by and large, we're really addressing how to predict what Lewis dot structure is going to be the best Lewis dot structure or the most stable. Of course, this most stable is the best Lewis dot structure. It's the best representation of the molecule. We'll talk eventually about how resonance structures actually, the molecule, if you really looked at it, we're able to see it in some way. It's not one or the other. It's a blend of the resonance structures, but the one that it's most like, or the resonance structure that best represents it, is actually the resonance structure that's the most stable. So overall, predicting Lewis dot structure stability becomes really important for us. To do that, I'm going to give you 4 rules, and I'm going to give them in order. So the first rule is the most important component of stability, moving to the least important component of stability. So let's get into it. All right, the first rule and the most important rule for stability is complete octets. If you have 2 Lewis dot structures, one doesn't have a complete octet and the other does, the one with the complete octet, of course, is the most stable. Now, before I move on, let me give you a quick overview of where we're going with this. I'm giving you the rules, and then we're going to look at them in practice a little bit. And then at the end, I may address one more time the reason why we're doing it, which I've already addressed briefly. So, complete octets is the most important. All right? Number 2 is the least formal charges. So we've already addressed formal charge a little bit in organic chemistry, but here I just want to tell you the one that has the least, this is why formal charge matters, the one that has the least formal charges or the least intense formal charges is definitely going to end up being the most stable after octets hierarchically. All right, so now number 3, the least charge separation. So this really ends up being important because whichever one has the least charge separation ends up being the most stable after these others. And that just means the formal charges, how far apart are they on the molecule? If they're very near to each other, they end up being the most stable. And actually, this ends up being because we can easily get rid of them with resonance and some other factors like that. So least charge separation. And number 4, a negative charge on the most electronegative atom. All right, so I'll give a sub point to this in a minute, but if you have a formal charge at all, or if you have electron concentration that's moving around, we want it to be on the most electronegative atom. But remember, this is after all of these others. So if all of these others are equal, then we would compare the two based on this 4th point. We don't get to that point even that often. And I'm going to give a sub point, but I'll tell you, we get to this sub point even less often. Of course, a positive charge on the least electronegative would also be important, but this is like the least important of all of them, and I've almost never seen us get that far when comparing Lewis dot structures. So let's look at a couple examples of these, and I want you to predict which one is more stable using our rules. So let me draw a Lewis dot structure and a resonance structure, and basically 2 resonance structures, and see what you think which one is going to be the most stable. So let's go ahead and draw what we call a carbonyl, which is a C double bonded to an oxygen like this. So here are 2 Lewis structures. I'm using the arrows to show and the red to show which electrons are moving and where they're moving to. So let's go ahead and take a look at this one first. So if we look at this, where are these electrons? Which one of these 2 is the most stable? Well, what do you think? Which one of these is the most stable? Make a prediction and then play it once you've done, and also tell me why that one is the most stable. Okay, what you should have gotten here is that this negative charge is, of course, a big hint, and by the way, I'm missing a charge here. There's also a positive charge on this carbon. So if we look at these, what we notice is that there is, all those charges don't even matter that much, because this one right here has complete octets, and this one over here doesn't have complete octets. So this one is the most stable on the left-hand side. Let's take another look at these. All right, so looking at this example, what do we notice? Well, let me go ahead and put the charges on here. Actually, you assign the charges, and then I want you to predict which one is the most stable, again, using our rules. So go ahead and pause, do that, and then play it. All right, what you should have gotten here is you should notice there's a negative charge here because there's only one bond on that oxygen. Remember our pattern, one bond on oxygen is going to be negative because it's not two bonds. And then here we have a positive charge. So if you look at that, are the octets complete? Absolutely, octets are complete on both of them. So we need to go to our next rule down, which was charges. Which one has the least formal charges? Well, as we notice, this one has the least formal charges. So this one is the most stable. This one is not stable as stable because it has formal charges, even though both have complete octets. All right, let's do one more example. All right, so taking a look at these two, this is a little more interesting, a little more complicated. I want you to go ahead and compare these. These aren't two resonance structures, these are two completely different molecules. And I want you to compare these two molecules and tell me which one is more stable. Now this ends up being important because where we're going with this one is we're going to predict which one of these is more likely, which is of course the one that's more stable. So please go ahead and do this one, and then I'm going to go through it with you, and we'll sort of talk about it. And I'll give you a real little hint right now. Look for resonance structures here. Look if there's any resonance structures possible, and that might help you. So go ahead, look for any resonance structures, draw them where you see them. Now pause, play, and we'll talk about the resonance structures, and then we'll talk about stability afterwards. So go ahead, pause that. All right, so what you should have seen for resonance structures is this. You'll notice that if you took these electrons, you could move them up to right here where there's this bond and form a double bond. So let me draw that structure for you, and we'll see why it forms a resonance structure. You'll notice there's now a positive charge there, all right? Now let's look at the other one and see, are there any resonance structures for the other one? What you'll notice is there are no lone pairs of electrons that can make it all the way over here. Lone pairs of electrons can only go from where they are here to form a double bond or vice versa. They can't move somewhere completely else, otherwhere on the molecule. So this is as far as they can go. This means that there is no resonance structure here. Now, really quickly, I'd like you to compare two things. First of all, A and B, which one is more stable? And then also as a part of that, I'd like you to compare these two molecules. And we'll call these 1 and 2, the two resonance structures of B. Tell me which one of those is more stable. So pause, play, and find out. Pause, make your prediction, play. All right, what you should have noticed here, which is really interesting, is that number 2, you right away look and you're like, yikes, there's a positive charge on that chlorine, which chlorine's really electronegative, right? But wait, that's rule number 4. What's rule number 1? Rule number 1 is complete octets. Well, is there an octet here? No, there's no octet there. Is there an octet here? No. No octet there. Is there an octet? Are all the octets complete here? Yes. So actually, despite that positive charge on the chlorine, which is really tempting to pick, we notice that this one actually is the best. This is actually the best. Between 1, 2, A, B, all of them, it has complete octets. This is the best Lewis structure. Well, that actually means that B is the better or more stable compound because it has a resonance structure. So a resonance structure already makes things more stable, but then the resonance structure is quite good. It has complete octets on it. So that is the summary here. We have these complete octets here, right? And we also have resonance, so this is the best structure overall, and B is preferred, so B would be the most likely outcome. Now I'm going to use this to talk about where we're going with this and why this matters. Now, In the future, I'll tell you a hint, this is going to be a problem we're going to look at. We're going to try to predict whether the carbocation would be more likely to form here or here. Where will it form, on the left or the right? And where the place where the chlorine is or the place where the chlorine isn't. And what you'll see, and I'll tell you in the future several chapters from now, is it's going to form on B because it's the most stable because of those complete octets, even though it's kind of hidden because it's a resonance structure down here, sort of obfuscated. So what I want you to practice doing is predicting these stabilities and also looking in the background for resonance structures, because that's what makes all of this work. So that's where we're going to go with this, and how to project Lewis structure stability.